Hello, and welcome to something a little bit different for me. I'm going to be talking about a specific feature of the C++ language, pointers. And I felt there was a need to do this video because on Discord and on YouTube and via email I've been asked quite a number of questions about people's code that doesn't work, and invariably the problem seems to lie with a misunderstanding of how to use pointers in the first place. So this is a little video I can use to, excuse the pun, point people in the right direction if they do have any problems with pointers. In my video output to date, I've never really targeted a specific audience, and I'm trying not to with this video either, so it doesn't really matter if you're a beginner or intermediate. Maybe there'll be something in this video that will be novel to you. And even for the non-C++ programmers out there, I'd still really recommend watching it because pointers are fundamental regardless of which language you're using. It just could be that other languages are hiding the fact that pointers are being used. So let's get started by asking the question, what are pointers? And fortunately, there is a very simple answer to this question. A pointer is just a variable that holds a memory address. I repeat, a pointer is just a variable that holds a memory address. If you've liked this video, give me a no, I'm only kidding. There's actually a lot more to it, but fundamentally it is really that simple. I'll start by just introducing the basic syntax. But fundamentally, it's important to know that whenever we're working with pointers, we're working with memory. And so here, I've drawn some random access memory, some RAM. And I've got a column which represents the addresses, so this is the location in RAM, and a column that represents the value at that specific location. I've not populated any values just yet. So let's assume in our program we have something along the lines of int a equals 5. We've asked the compiler to make sure that our program will have enough memory to store a variable called a and give it the value 5. Now, we know that variables of different types have different sizes. We'll not worry about that too much here. And so just to calm down the masses, let's assume that all the values are 32-bit. When we write something like this in our program, we don't really have any control over where it goes in memory, and we don't care either, because what we care about is that we can represent that location in memory through this variable name, a. So let's say the compiler has gone and used memory address location 102, which will stay is a, and it's given it the value 5. So loosely, in our program, wherever we see the variable name a, what we really mean is go to somewhere in RAM and look up address 102, which corresponds to a, and return the value 5. So to all intents and purposes, the variable name disappears. And this situation is known as direct addressing, where we take a symbol and it directly corresponds to a location in the RAM. Now, as discussed, a pointer is just a variable that holds a memory address. So in our simple system here, let's create a variable type pointer, and we'll call it b. Just as it did with the integer, the compiler will go and somehow structure our memory so that b is stored somewhere in it. So let's say here, b is stored at address 104. We've had no control over that, it is where it is. But the value b holds is going to be a memory address. So we could declare it explicitly, b equals 100, for example. So the value goes to 100. What I'm trying to demonstrate here is there's absolutely no difference between the two things. A pointer is just a variable that holds an address in memory. It's very rare that we'll actually set the value of a pointer explicitly and numerically like this. Instead, it's more useful to use the location of an existing variable in the program as the value that we give to the pointer. And C and C++ provide something which is the ampersand symbol, which behaves like get the address of a variable. So here we've said our pointer, b, we want to set its value to be the address of wherever a is stored. So in this case, we can see a is stored at address 102, so the value stored in pointer b is 102. Now that we have a location in memory that stores a value which represents a memory address to a different location, we've implemented something called indirect addressing. And so whereas we had an operator that allows us to get the address of a variable, we can have an operator that allows us to get the value at that address. So let's create a third variable, int c. but I want to get the value from the location pointed to by b. And in C and C++, that's the asterisk operator. Confusingly, not multiply in this case, but this means get the value at. So we want to get the value at the location pointed to by b. So how will this be interpreted? Well, the compiler will have created the symbol C somewhere in our memory, but what we're saying is please get the value at the pointed to location of our pointer b. So we'll look at the value of b, which is 102 in this instance, and we'll use the value of b as an address of the actual value we're interested in. So this 102 points to a effectively, which is what we've set up here, and we'll get the value 5. We have indirectly set the value of c to a using a pointer, b. And that really is all there is to pointers. As I've stated, and I will state many times in this video, they're just a variable that holds a memory address. But even in this simple example, we've started to see some confusing syntax. We've introduced two new symbols. Now, the address of symbol, fair enough. But we've started to use the multiply asterisk to represent get the value of. And I think it's this usage of additional symbols that makes pointers quite confusing to those that haven't seen them before. And in fact, it gets even more confusing, because there is no variable type called pointer. As we'll see in the following practical examples, it's important that the compiler and the programmer know what type of information the pointer is pointing to. So we have to include the type somewhere in our pointer definition. But clearly we need to include something else, because this is now saying that b is just a type integer, no different to a and c. Well, in C and C++, to say that this is a pointer to an integer, we include the asterisk symbol again. So we can read this as saying, please create a variable that holds a memory address to another variable that is an integer. And sometimes you'll see it written out like this, and sometimes you'll see it written out like this. Both are valid. But C and C++, we're using the same symbol again to represent something else. So now it represents please declare me as a pointer, and here it represents please get the value pointed to by this pointer, and when it's not in the context of pointers, it means multiply. Fortunately, as long as you get into the habit of thinking methodically about how pointers are constructed, you won't get yourself into too much trouble. It's quite important that pointers know what type of data they are pointing to, and this is why. So let's assume we're now working with 1 byte per location in our memory address, so 8 bits. We know that in a C and C++ program, more or less all the time, an int is going to be a 32-bit value. So our compiler will go and allocate some memory for variable a, but it'll take up 4 locations. So let's assume it sticks it here at location 100. Our 32-bit variable will take up 4 locations in RAM. So let's just denote these as A0, A1, A2, and A3. If I create a pointer again, so int star b equals the address of a, and this time let's assume that b has been created somewhere else in memory. It's given the value 100. If I were to increment the pointer, so b equals b plus 1, giving me the value 101 is not that useful, because now I'm 1/4 of the way through an int. What is typically more useful to the programmer is to move in a whole int step. So incrementing the pointer by 1 like this is really the same as saying b equals b plus the size of, in bytes, of an integer, which is the same as saying b equals b plus 4 on our system. So our original b value pointed to the memory that represents this integer. If we increment it once, we then start to look at the memory that represents the next integer. And this is quite useful. But before we get ahead of ourselves, let's look at some practical examples. I've created here an absolute bare bones program to help explain the basics of pointers. And I'm going to introduce pointers by first talking about arrays. So here I've created an array of 10 integers called SumArray. I'm not even bothering to initialize it. And the reason I've chosen to use an array is that in this situation, the compiler will create an array which is contiguous. And this means that the memory that will be used for this array will be complete and whole. There'll be no gaps in it, nor will there be any obstructions. There'll be a single solid block of memory allocated to implementing this array. In this case, it's 10 integers. And we know that integers are 4 bytes, so we would expect 40 bytes of memory uninterrupted to represent this array. Here I've created 2 pointers. We can see the integer and the asterisk symbol, indicating that I'm creating a pointer of type integer. I've called this one location 6, and I'm going to point this pointer at element 6 of the array that we've created. So standard array notation here, grabbing the 6th location in the array, and I want the address of it. So there's the address of operator. And I've done exactly the same, another pointer, this time going to location 0, which is the start of the array. I'm now going to do something a little strange. I'm going to display the value of the 2 pointers and also the difference between them. Let's take a look. Well, here we've got 2 numbers and the difference between them is 24. Location 6 is 24 larger than location 0, but the difference is just 6. Well, this makes sense. If we've got 6 positions in contiguous memory apart from each other, and each one of those positions represents a 4-byte thing, in this case an integer, then we've got 24 bytes difference between the 2 locations, and this is exactly what we saw as the difference between the 2 numbers. But when we subtract location 0 from location 6 as pointers, it returned the difference, in this case, in whole integers, which was 6, which is fair enough. Now I'll run it again. This time we'll see the numbers are different, but they still differ by 24. And the only reason I'm showing this is to emphasize that you don't really have that much control over where things go in memory. Run it one last time, again, different numbers, and the difference is 24. So the fundamental distinction to make here is that the memory addresses work on a per byte basis. But the pointers themselves, well, they work in a space defined by the type of object that they are pointing to, in this case, an integer. We see that we declare a pointer by including the asterisk at the start, and we've used the address of operator to get the address of something. In this case, it happens to be location 6 in this array. Now I know to some of you that may have gone well over your head, but persevere because I'm going to show some other examples, and I'm also going to show situations that can catch out the unwary programmer. And I hope by the end of this video it will all sort of gel together and you'll start to get the bigger picture. I'm now going to give our array some values. So I've given it 10 values, which is just multiples of 3. And I want to demonstrate different ways of accessing the same data. So I'll get rid of this. Here we're using the address of operator of a location in the array. In this case, it's the 0th location. We want the very beginning of the array. Well, arrays don't have any precursory information attached to them, so the 0th element is really the start of the memory that was allocated for that array. Which means we in fact don't even need to do this. We can simply say that our location, pLocation0, equals SumArray, because SumArray is in fact a pointer in disguise. And you can see no red lines, the compiler is quite happy to accept this. However, I'll just put that back for clarity. Let's display the contents of the array. Just to prove that it works. But let's look at different ways of doing the same thing. Now we know a thing or two about pointers. We know that SumArray is just a pointer. It's pLocation0. So this should output a memory address 10 times. Since we know SumArray is the same as the 0th location of the array, we can use pointer arithmetic to add an offset to it. So in this case, I'm going to add the I value. So we'll take the 0th location of our array pointed to by SumArray, and we'll add 0, 1, 2, 3, 4 to it. Let's take a look. Well, we can look at the numbers this time and we see that they differ by 4 each time, conveniently the size of an integer. So if that's our memory address, we should also display the value. So I'm going to put in just some friendly text, but this time we want to get the value at that location. So SumArray plus I, but if you remember the value of operator is the asterisk. Let's take a look. And this time we can see it is now displaying the contents of memory at that location. yet we've not indexed it like an array at all. Don't forget, a pointer is just a variable that holds a memory location. So here is that variable, and we're incrementing that variable and displaying the memory location. But we're using the value of operator to return the value stored at that memory location. We can do similar things in a slightly different way. We know p location is the start of our array. So let's output that value. And we'll also output the data stored at that location, as we've just done. So here we've got the address, and here we're using the value of operator to return the value. But this time I'm going to increment our pointer each iteration of the loop. Let's take a look. And as expected, we see the memory addresses and the values at that memory address. I'm just trying to demonstrate the flexibility you have with pointers and pointer arithmetic. Let's just briefly examine why pointers may have a reputation for being more complicated than they are. Let's consider the same example as we've just seen, but this time instead of it being an integer, I'm going to use a type char. And instead of an integer array, it's an array of chars, it's a string. Hello. Other than the type change, we can see everything is just the same. And as we did in the very first example, I'm taking 2 pointers to 2 locations, and I'm going to display them. Let's take a look. So we're printing out what the string is. We've got 2 memory addresses. In this case, they're only 3 apart, and it says the difference is 3, and that's because a single char is a single byte. That makes sense. But let's see what happens when we take these casts out of the location values. Well, we start to see something a bit weird. We see the 2 strings, but we see fragments of them. In fact, location 3 starts from the 3rd element of the string. And location 0 clearly starts from the beginning of the string. And this is very confusing. Let's say we didn't actually initialize it as a string, we just initialized 10 bytes of char. And now we run it. You know, things are just getting worse here. What's going on? And that's because when you see chars and pointers of chars, it's very common that you're actually inferring a string. And so there's quite a lot of operators amongst many functions across C and C++ that expect to see pointers of type char representing strings. And so they do string-specific things. So in this case, this char star location 3 is being treated just like a regular string. That's why we're not seeing the value of the address here unless we explicitly cast it to an integer. So just a little bit of a trap for new players, some functions are expecting pointers and will behave differently depending on the types of pointers they receive. Right, now for something a bit different. I'm going to create an object, some object. The object has 2 fields, x and y, and I've declared that x and y be initialized with these values, a3, a2, a1, a0 in hex. I don't really care what the numeric value is here, I'm more concerned about the hex symbols being used, because we're going to use the debugger to look at how this object is moved around in memory. If we wanted to create one of these objects in our program, the easiest way is to simply declare it. And if we wanted to create an array of them, well, we'd stick a value at the end. This is really basic stuff. And when we do this, we have actually created this memory on what's called the stack. It's known at compile time what is required here. So the compiler can go and deal with it all for you. So let's just take a quick look at that running. But I'm going to use the debugger. So I've run to the line, and what I can see, I may try and zoom these windows so they're a bit more clear for you. But when we create the object, pSumObject, we can see that the pointer value has become populated. And we can take the pointer object and drag it onto a memory window and actually have a look at the memory. And so we can see here that our simple structure of 2 types of integers is A0, A1, A2, A3, B0, B1, B2, B3. And we'll see that repeated 10 times. It's exactly what we needed. I got a little curious at this point and decided to add in a constructor, because I wanted to test, was the compiler actually going to call the constructor of the object? Let's take a look. So I run the code, grab my pointer, bring it over to the memory window, and we can see, yes, it does. In fact, whilst it's allocating all of those objects for that array, it's calling the constructor. Because now we see C0, C1, C2 instead of A's and B's. Now this is great if we know in advance how many of the objects we're going to need. But what if we don't? Well, instead of using the stack allocation, we'll allocate on the heap instead. And we'll need a pointer to do this. Here, as we've seen throughout the video so far, we've created a pointer. And this pointer is going to point to the 0th element of our array of 10 sum objects. And that's because the new keyword will return a pointer. We don't know where the OS is going to put this array, but we need to know where the start of the array is, so it makes sense that we have a pointer that represents that location in memory, because a pointer is just a variable that holds an address in memory. And so this is quite a useful technique for runtime allocation of memory. But let's take a look how these objects get constructed. We'll run the debugger. You can see right now that my pointer has no specific value. If I drag it over to the memory window, it's undefined. We can see the debugger has returned a pointer and given us the memory address value, and that the data pointed to at that address is what we expect it to be. So far, so good. Nothing is any different. However, whenever we request memory from the operating system at runtime, it's really good practice to give it back. So we have to clean up after ourselves. But fortunately, we know where the object starts in memory, and we can call the delete operator, because we have a pointer that points to the start. Now, let's get all meta. Let's make things really complicated. What if I wanted an array allocated at runtime, and it was an array of pointers rather than an array of objects? We want to get a pointer to the start of an array of pointers, and we're going to create, using the new keyword, just our pointer objects. So these are 10 memory addresses being created now, rather than 10 objects. So let's take a look at how this gets constructed. Let's run it, and we'll drag the pointer over to the memory window, and we see CD, CD, CD. Oh dear, right, it's not quite done it. In fact, what it has done is allocated enough memory for 10 pointers. Of course, it's not constructed the objects. We need to do that individually. CD is one of the cryptic values used by the Visual Studio debugger to say, hey, I've not been allocated yet. Instead of CD, we can force it to use a value, 0 in this case. Now I prefer this notation to say, please initialize my memory all to zeros. So this time, if I drag the object over to the memory window, we can see it's initialized it all to zeros as requested. There is an alternative to this notation, which is to use an open and close parenthesis. I don't like this as much because it looks like it should be a function call. That's why I prefer the explicit curly braces. So now I have a pointer to an array of pointers. For each element of that array, I want to create a new object. So let's take a look. Drag over the pointer to the memory window, we can see our zeros. So the first one gets allocated, second one gets allocated, third one gets allocated, but these aren't C's and D's that you were looking at before, or A's and B's. These are, in fact, memory addresses in their own right. Because don't forget, pSumObject is a pointer that points to an array of pointers, and pointers are, we all know this now, all sing along, pointers are just a variable that holds a memory address. In situations like this, the cleanup also becomes more complicated too. And I'm going to sort of emphasize it's important to clean up after yourself. So once you've done some stuff, you then need to individually erase all of those objects. The overall array delete, this one, will only delete the array of pointers, but the objects themselves still need to be deleted individually. There we go, much better. Now you may be asking yourself, why on earth would I need to do something completely as bonkers as this? And well, one of several valid answers is polymorphism. Now, if you haven't got a clue what that means, that could well be the topic of another video, or at least go and have a look at my Code It Yourself role-playing game series. We used polymorphism a lot to implement that game. And if you haven't got as far as polymorphism in your programming journeys just yet, don't worry about it, you might pick up a thing or two in this very simple example. Really briefly, polymorphism is the ability for one object to behave and look like another. So I've created a very simple object here called SumBaseObject, and it's got one method, which returns a string that identifies what the object is. I'm going to create an additional 2 objects that inherit from this base object, and they override the same method. So subobject A will identify itself as subobject A, and I'll add a very similar subobject B. So a base class, base object, and 2 subclasses of that class called subobject A and subobject B. Instantiating any of these objects is very simple. There's the base object, we'll create a variable called obBase. Likewise for the two sub-objects. And here I call Identifier Self on all three objects. Let's take a look. Perfect. Each object has identified itself. Let's suppose I want an array of objects, and I want to iterate through that array one by one and get them to identify themselves. Well, I can create an array of 10 base objects and create a loop that loops through all 10 and calls the Identifier SelfFunction. And if I quickly run that, we'll see we get 10 base objects. Very good. But how do I set one of the objects to be one of the sub-objects? So let's pick object 3 here, and I want to force that one to be object A. Now object A is a subclass of the base object, so that's legitimate. That's why the compiler is not complaining. But the wrong Identifier Self method is called. We might be able to fix that by adding in a virtual keyword, which tells the compiler that if I am subclassed and any of my children happen to override this method, please call the child's method instead. Let's take a look. And it doesn't work. And that's because our objects, crucially, are some base object. It doesn't matter whether it's a child object or not, the array only consists of some base object. What we want really is a structure that allows us to have a mixture of base objects, object A's and object B's all in the same array, and let the compiler intelligently work it all out as to which method should be called on which object. So let's get rid of this. And bring in our pointer to an array of pointers. In this case it's an array of pointers that represent our base object. I'm only doing 5 of them. And as before, I'll get all 5 of them to identify themselves. Now, we're using pointers now instead of actual objects, so we need to change from the period symbol to this arrow symbol. And just before I get slammed for really bad practice, I'll also clean up after myself, so I'm going to loop through all 5 and delete the individual objects and then delete the overall array of pointers. So after I've allocated my array, I then need to create each of the objects individually. I need to do this 5 times. 1, 2, 3, 4, and we'll have a mixture. So we'll say that one's going to be B, that one's going to be B, we'll keep that one as A at the end, and we'll have base object as well. So now I've got 3 different types of object being created in a single array. All of these objects implement an Identifier SelfFunction, which means that these sub-objects can have any kind of crazy implementation and additional functionality that they want. As long as they provide an Identifier SelfFunction, it will all be okay. So let's run this. And here we can see our array only consists of one type of object, the base object, yet individually those objects are unique. And this is a really powerful tool in object-oriented programming. What we have avoided is the need to manually try and work out what each type of object is, for example having a big if statement or a switch block or something similar. Through the use of pointers, the compiler and executing subsystem is capable of just sorting it all out for us. Perfect. Now I'm getting a bit long in the tooth, and I'm aware that arrays aren't very popular at the moment and people prefer to use vectors instead, but exactly the same thing applies. We just add the new elements to the back of the vector. For the Identifier SelfFunction, we'll use an auto for loop. And we'll also do something similar for the cleanup code. Because it's important to remember that when you're deleting a vector, all you're doing is deleting the outside container. You're not freeing up the memory internally. So I do want to go through all of the elements of the vector individually and delete them. What's interesting about this loop is the introduction of the address of operator here. And in this instance, it's referring to pass by reference. Normally when you would iterate through a loop without this operator, A would contain a copy of whatever is in that vector. We don't want that. We want the actual thing that is there. We want a pointer to the location in the vector. So we want the address of. So any changes we make are to the actual data in the location where we expect it to be, and not a copy of it. And once we've deleted all of the elements individually, we'll clear the vector. Let's just have a quick look through the debugger at this and see what happens. I've got the vector here, the size is set to 5. It's got 5 things in it. And each one of those things is a pointer to an object. I'll expand them there. And as we go through each iteration, we can see that the pointers are being invalidated each time. But what we haven't done is change the size of the vector, even though we have deleted the elements. The size is still the same. So the vector contains nothing now, all of our memory has been cleaned up, but the vector itself still exists. So we'll call the clear function to get rid of all of the structure that represents the vector. So you might be thinking, why is he banging on about vectors? Well, let's just simplify the situation completely. We have a vector with just an object in, no pointers at all. I'll put the object in. In fact, I'll put a bunch in, but I'm not creating pointers or anything of the sort. One of the most common problems I've identified with people's code is that they are doing something they shouldn't be doing, and that is creating pointers to elements of the vector. And this is completely legal to do. So you can see here, I'm creating a standard pointer to base object, pointer to vector element, and I'm taking the address of a particular location in the vector. And this is really, 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 really bad. Please don't do this, guys. It's not very often in a video I say you should or you should not do this, but this is one of these things you should not do. Never do this. This is bad. And I think the confusion starts because a lot of newer programmers treat vectors just like they're arrays, and they are not. Here I have some RAM, starting at 0, going off to, whatever, 16 gigabytes. Our RAM consists stuff from lots of different programs. So this area might be used up by the operating system, and this area may be used up by some other programs that are running. There might be nothing in this area, and then we've got another area here with something else, some other program, Discord, why not? And then I've got to make it, here we've got Chrome, using up, well, whatever's left. When we ask the compiler to create an array for us, say int a10, what we're saying is, please go and find a block of memory for us that's contiguous and return the starting address of that location. So, for example, it finds maybe the first available block of memory that it can, which is here. So if that is, for example, location 80, it goes to 120, assuming we're working in bytes. 40 bytes, 10 integers. If we requested a whole bunch of integers, say many thousands, that couldn't actually fit anywhere in RAM, it would fail. You'd get an exception. Vectors are quite deceptive because they look like arrays. So I could have a vector that stores ints, and the first time we push something back to the vector, it stores it in RAM. So that's very easy, and we know that we can access that as B0. That's a bit too similar to an array for my liking. Fine. As we add things to the vector, we add more and more things to the RAM, and we can keep accessing them because we're assuming the vector is contiguous. So we get up to a point, I don't know, 8, whatever, it's fine. But now we've run out of space. If we try to push back into the vector another integer, it can't do it. But it has to remain contiguous. That's what a vector should do. So what happens is the vector becomes sensitive to this and says, well, I'll just relocate my entire contents to somewhere where I can be contiguous. So on the 9th iteration, it will take all of the contents here, find some space for it, maybe it puts it here, copies it all over, and adds the additional new element. And this is why it is bad to have a pointer to the element of a vector. Because the pointer originally pointed to the 8th element here, and that stored whatever address was necessary to represent that element. But all of the contents of that vector have now moved, but our pointer still points to this original location. It doesn't point to the data it thinks it's pointing at anymore, simply because our vector has grown. What's even worse is it's very possible that the data in this original location has remained untouched and still looks valid. So actually identifying that something has gone wrong could be a very tricky bug to trace down. In short, never create a pointer to the element of a vector. You can do it, it is legal, and if you are in full control of everything that's going on in your program, for example, you may only be creating the vector once at the start of your program and never touching it again, then you can think about it, but on the whole I would suggest don't. So far we've looked at the very basics of pointers, we've looked at pointers and arrays, we've looked at getting the addresses and the values of certain locations in memory, we've looked at doing pointer arithmetic, and we've looked at the role pointers play in polymorphism. We've also seen some things that you should be wary of when using pointers. And that whenever we create memory dynamically using a pointer, we need to be responsible for cleaning it up, or else the system will simply run out of memory. Unlike other programming languages, C and C++ does not have what's called a garbage collector, something looking for objects that no longer have an owner. And more recent versions of the C++ standard have provided mechanisms to help address this. And these are somewhat confusingly called smart pointers. And I'm only going to briefly talk about smart pointers here. Smart pointers have been introduced to imply the concept of ownership of memory that is allocated. And there are two fundamental types that you'll see most often in C++ code, and the first one is the shared smart pointer, which allows multiple things to access the data that is pointed to. Personally, I'm unsure about smart pointers. They do have their uses and they can be quite convenient, but I don't like anything that encourages the programmer not to think about what they're doing. I like the fact that when using pointers you have to be responsible for allocating and deallocating your own memory. It makes you think about the journey the data takes through your program. Smart pointers alleviate that need to think about it. You still do need to be cautious using a smart pointer, but the idea is when everything is done using a particular piece of memory, it will delete itself. And it just doesn't sit right with me, the idea of encouraging the programmer not to have to think about things. As you can see, I've brought in the struct that we used towards the start of this video. SumObject. And I'm going to create a shared pointer. And it's quite wordy. Shared pointer, and it's a template, so we need to give it the object, and we'll call it SPSumObject1, and we need to use the command make_shared, which is effectively similar to our new command, and again it's a template, so SumObject, and we don't have anything to pass into the constructor of the object. Right, so that is the equivalent, smart pointer equivalent, to just doing new and a pointer. Fine. And if you're being really modern about it, you wouldn't have the using namespace std at the top of your program, and it would be twice as long. What I'm going to do is fake some scope in the program by using some curly brackets. And we're going to have a look at the behavior of a shared pointer as it goes in and out of scope. So we'll create an object within the bounds of scope 1 here, and we'll create a second pointer that points to that object in scope 2. Let's use the debugger to see what happens. So the object has been created, and we can see here SPSumObject1 has some data that looks like our object associated with it. Trouble is with a smart pointer is they don't look as simple as regular pointers. So if I grab the pointer and drop it in the memory window, we can see our C0, C1, C2, D0, D1, D2, etc. Perfect. If we look at the control block of the smart pointer, we can see another variable, uses, and that tells us it's been used once. We've now entered scope 2, and we're going to create a second pointer that points to the same location, the same object. Nothing new has been created in memory, but the number of uses has doubled. The smart pointer is now aware that two things are pointing to this location in memory. As we leave scope 2, we can see the uses has decreased. It's gone out of scope, this object has been removed from the stack, and as it's been removed, its destructor has been called, and that has decreased the count. The same thing now will happen as we go out of scope 1, the uses will go to 0, and when that happens, the memory that is pointed to by the smart pointer is deleted. And we can see here in the memory window, it's all been set to all Ds, which is a debug Visual Studio speak for deleted memory. So as a programmer, I've not really had to think about deleting and cleaning up my own memory. It does it for me as things go in and out of scope. There is a second type of smart pointer called the unique pointer. And this means only one thing can have access to the object. And in fact, it's so smart that it won't even let you compile things that invalidate the rules it has to follow. So here I've created a unique pointer to our object. Instead of make shared as it was before, it's now make unique. And as I did before, we go into a second level of scope. I try to point a second unique pointer at the same object, and the compiler doesn't like it at all. It's not that you get the most sensible of error messages, but you can tell something is wrong. It's now going to force me to think about, well, hang on, ownership has to be transferred here. Only one thing can point to the object. And in this case, you would use the move command, which stops it being owned by one unique pointer and transfers the ownership to the second one. We'll have a look again with the debugger and see what happens. I've executed the first line, which has created the object and created a unique pointer to that object. Drag over to the memory window and we can see the object certainly does exist there. I'll now execute the next line, which will transfer the ownership of the object from the first unique pointer to the second unique pointer. And we can see that the memory has remained unchanged. Nothing has become deleted, but UPSumObject1 is now set to empty. It doesn't point to anything. Whereas UPSumObject2 now points to the original object. As we go out of scope for the second time, there is no further transfer, so at this point the data should be deleted. And we can see, indeed it has, because only one thing is allowed to own that object when it is created uniquely. And so there you have it. I think I've covered all of the most basic uses of pointers in C++, and we've even had a quick look at smart pointers. There is no code for you to look at on the GitHub this time, but if you found this video useful, please give me a big thumbs up, come and have a chat on the Discord, have a think about subscribing, and I'll see you next time. Take care. Oh, and just before I go, a pointer is just a variable that holds a memory address.